Okay, so hello everyone, and let me double check if my slides are showing here. And sorry for the delay. Okay, so okay, great. So I also see the slides showing. So today we will continue our discussion on the generating functions, and then what? And then we are still talking about how to use the EGF exponential generating function to count the number of permutations. So as we recall, so if we are looking at permutations, and then this permutation is made up of mixing and arranging different types of items, then we can first create a EGF for the individual items, and then use rule of product. We multiply them together, so we will get the EGF of the arrangement of the mixture of these special items. Okay, now, so let's look at another example today. So suppose that we have this time n kinds of objects, and then each of them has unlimited supply. So if we look at one particular object, the corresponding EGF will be this one, 1 plus x over 1 factorial plus x squared over 2 factorial up to x3, so up to whatever. So this bracket sign is 1, so forget about this to the power n. This thing is the EGF for one particular object because there is exactly one way of choosing 0 of this type of objects. There is exactly one way of getting one of these objects, exactly one way of getting 2 of these objects, and so on and so forth. So for each particular object, the exponential generating function will be this one, and this is exactly e to the power x. And then this time we want to get the permutation of n kinds of objects, so we just multiply the EGF of them, so we will get e to the power nx. Okay, and then e to the power nx is what? So if we use Taylor's expansion or whatever, so we will get that this is summation of n to the power r divided by r factorial x to the power r. We sum them up for all the cases of r equals to 0 up to infinity. So we will see that, okay, the coefficient of x to the power r, if you multiply with r factorial, this gives the number of permutations where we have altogether selecting r objects. So altogether r, the length is r, and then the ordering is important. So how many ways are there? So there are going to be n to the power r. Is that okay? So we get the coefficients multiplied by r factorial. This is the desired number of permutations. Okay. Now, if ordering is important, okay, so here, so this is the EGF. Okay, so this is what we get. Now, how about a more? So let's see another example. Okay. So this is an example that, or some similar example we have done previously, but let's see. So let's consider we are getting an R digit quaternary strings. So altogether we are selecting R. So the length is R. But then for each position, it can be 0, 1, 2, or 3. So what does that mean? So we are actually looking at 4 types of objects mixing together. And then we have extra requirement. Here, the requirement is we will need to have containing at least 1, 1, and at least 1, 2, and also at least 1, 3. So there is no restriction about 0. So we want to find out what is the EGF of the whole system. And in order to get the EGF of the whole system, we can get the EGF of the individual part. So what is the EGF when we focus on the digit 0? What is the EGF for the digit 1, the digit 2, and the digit 3 respectively? So it is rather simple. For 0, because there is no restriction, it is the same as what we have just discussed. It is going to be e to the power x. Now the EGF for digit 1 is e to the power x minus 1 because we will need to have at least 1, 1. So there is no way, there is 0 way to choose 0, 1. But then there is always 1 way to choose 1, 1, 1 way to choose 2 ones, 1 way to choose 3 ones, and so on and so forth, when we just focus on the ones. Okay? And similarly, the EGF for digit 2, digit 3, they are both e to the power x minus 1. So in that sense, we can obtain the EGF of the whole system. So when we try to mix the 0, 1, 2, 3 together and then form arrangements, so this is going to be the product of their individual EGF. So we multiply them together, we get this one. So once we get this one, then what do we know? So in order to find out the original question, so we get the EGF for counting. So in order to get the original answer, so we are focusing on how many ways are there to get the length R digits quaternary strings. So what we should do is we should look at this EGF, find out what is the coefficient of x to the power r, and then knowing that the answer that we want is the coefficient multiplied with r factorial. So after doing this checking, so the coefficient of x to the power r here is 4 to the power r divided by r factorial. So once we multiply this with r factorial, we get 4 to the power r here. And similarly, the coefficient of this term, when it is multiplied with r factorial, we get 3 times 3 to the power r and negative. And for this one, plus 3 times 2 to the power r. And for this one, this is e to the power x. So the x to the power r coefficient is always 1 over r factorial. So when it is multiplied with r factorial, we get minus 1 here, the minus 1 here. So we get the desired answer like this. Okay. How about another example? So this is exactly the same example that we have studied when we are talking about the permutations or combinations part. So this time, we want to find out how many R-digit quaternary strings that contains even number of zeros. So we have done this before. If you still recall, the total number of them that contains even number of zeros should be something like 4 to the power r plus 2 to the power r, and then we divide this by 2, something like this. Okay. Okay, but let's see. So at that time, we are making, we are getting the answer by using a combinatorial argument. But here, we are trying to solve this with brute force, mechanical calculation. So what we need to do is, okay, we are getting the EGF for zeros, EGF for ones, EGF for twos, and so on and so forth, and then get the answer. Okay, so we will get the EGF for the whole system and then analyze what is the coefficient of the x to the power r term. Okay, so here it contains 2 questions. So the first question asks how many of these R-digit quaternary strings has even number of zeros, and then the next question says how many of them contains even number of zeros and at the same time also even number of ones. Now even number of zeros, what does that mean? So it means that there is 1 way of choosing no zeros, 0 ways of choosing 1, 0, 1 way of choosing 2 zeros, 0 way of choosing 3 zeros, and so on and so forth. So the EGF for the zeros should look like this: 1 plus x squared over 2 factorial plus blah blah blah. And then this one, we can relate this with e to the power x and e to the power minus x. So we can obtain this by averaging e to the power x and e to the power minus x. So we get this one is actually this one. So once we have something like this, we can obtain, what? We can obtain the EGF for 0 and then also the EGF for 1, 2, 3. They are all e to the power x, right? Because there are no restriction. So in the end, for the whole system, in this first part, the EGF will be something like e to the power 4x plus e to the power 2x, and then we divide this by 2. So in that sense, the desired answer will be the coefficient of this one multiplied by r factorial. So we get 4 to the power r plus 2 to the power r and then divided by 2. Okay, so we get the solution for this one. Now for the next one, for the next one, it is also easy. This time we get the EGF for 0 and then EGF for 1. They are both e to the power x plus e to the power minus x divided by 2. So we have multiplied them together. So we get the product of them. And then multiply them with e to the power 2x. So we get the EGF of the whole system. And then we can analyze the coefficient of x to the power r and then derive the answer. Okay, so this is finding even number of zeros, right? So how about odd number of zeros? So what will be the corresponding EGF? And then can you express this EGF based on EX, E minus X, and so on? So this is something that I will leave you as a challenge, okay? Now the next one, the next one is a strange problem, okay? So this time we are asking you to relate what you have studied so far, and let's see if you can formulate the EGF for the counting problem here. So here we have a sequence. We have A0, A1, A2, or something like this, up to whatever. So we have AR that corresponds to the way of selecting our objects or fewer. So altogether we have exactly our objects. But then how many ways are there to select them? But we may not be using every one of them. And then we are going to put these objects into n distinct cells. And then the objects inside the cell, the ordering matters. So which one is put as the first object in a certain cell, which one is put as the second object in a certain cell, it matters. So how many ways are there? So here we want to show that, so here this problem we are not actually counting AR, we just need to show that we want to show that the EGF for this system is this one, okay? So if you watch the OCW recording that was taught many years ago, so I don't have a very good idea of what it is going on. But after so many years now, there is a better understanding for this problem, okay? So for this problem, so what you can do here is you just first imagine that you have R digits. So you have an R digit string, and then for each digit, we are going to put a number between 0, 1, 2, 3, up to n that corresponds to, if it is a number between 1 to n, so it is meant to say that this particular position or this particular object is going to be put into the corresponding bin. And if it is 0, then it means that it is not going to be selected at all. So here we are actually finding how many arrangements are there, and then making sure that if there are, let's say, various items from the same bin. So for instance, maybe item 2, item 4, item 5, they are going to be put into cell number 3. So we will put the 3 at the second position, 3 at the fourth position, and 3 at the fifth position. Then it doesn't just say that it is not enough to denote the actual scenario. So we will first tell us that, okay, they are put into bin or cell 3, but we will also need to specify which one is put as the first one, which one is put as the second one, and which one is put as the third one. Okay. Now we want to get the EGF for the whole system so that we can count the number of arrangements. So the EGF for 0 are items that we are not going to select at all. So the ordering doesn't matter, we just do not select them. So the EGF for those zeros is very easy. It is just e to the power x. Is that okay? Because if there's just no 0, there's one way of doing so. If there are 1 0, there's just one way. If there are k zeros, there's just only one way of putting the zeros, arranging the items there. But on the other hand, when we talk about the EGF for 1 represents which items are put into cell 1, okay? So in that case, suppose that there are k items that they are selected to be in cell 1, then in that case, because the arrangement of them matters, so there will be k factorial of them when we are selecting k items. So in that sense, the EGF for the first bin, for the digit 1 here that we are going to fill in, will be 1 plus 1 factorial over 1 factorial times x plus 2 factorial over 2 factorial times x squared plus 3 factorial over 3 factorial times x cubed, and so on and so forth. So it is exactly 1 over 1 minus x. So in that sense, e to the power x represents the case for arrangement of the type 0 item. And then each of these 1 over 1 minus x corresponds to the arrangement of the type 1, type 2, up to type n items. So in that case, we get the EGF for this one. Now, actually, once we have this EGF, then we can find out what is the corresponding coefficient of x to the power r here, and then multiplying the result. So it is fairly easy, yeah, because each of the term here is easy. This is e to the power x, and then this is equal to 1 minus x to the power minus n. So I'll leave this for you to think about this now, and then later I will put the answer of the AR here in the discussion announcement. Okay, so you can try to find out what is the value of AR that we want to find it here. Express it in the simplest form in terms of n and r. Okay, so next one. Okay, so we are going to talk about some related topic now. So this time we are going to put objects into cells, and then, but here we are going to distribute objects into positions, but this time we are starting something new. The boxes, the cells, or the bins that we're looking at now will now be more complicated. So they will now be non-distinct. Okay, so here in this part, we assume that we are going to put objects into non-distinct boxes. But then objects in themselves can be distinct or non-distinct, so we will divide it into two cases. So the focus of the remaining part here are putting objects into non-distinct positions. But still, we may still rely on our knowledge of how to put objects into distinct positions to help us to do the analysis. Okay? Okay, so here, so again, as just mentioned, we want to do non-distinct positions, but let us review what if we are putting objects into distinct positions. So we are talking about distinct objects into distinct positions first. Okay, so suppose that we have R distinct objects and distinct cells, and then each cell can hold any number of items. All the items have to be used, so the number of ways is n to, if the ordering doesn't matter, so the number of ways is n to the power r. Is that okay? So we just need to decide for which object, which bin that we are putting it into. N choices for each, so n to the power r. Okay, now another case. So this time, suppose that we have more objects than cells, and then each cell here is still distinct, but we have a restriction. Each cell must contain at least one object, and then all the objects has to be used. So again, assuming that the ordering doesn't matter, so how many ways are there to put them? So this is the EGF problem that we are studying. So what we are looking at here is, so the number of ways. So let's say n is fixed. Okay, let's say n is fixed. So what will happen? So we are looking at R objects, and then for each object we need to give it a label 1, 2, 3 up to n, and then we want to have a restriction that for each label it has to appear at least once. Okay, so the number of arrangements will be, we can get the EGF for each label. EGF for label 1 will be e to the power x minus 1, EGF for label 2 will also be e to the power x minus 1, and so on and so forth. So we get the EGF for each label so that we can get the EGF of the whole system. And then the desired answer will be the coefficient of x to the power r when it is multiplied back with r factorial. Is that okay? So here, yeah, this is what I want to mention. So the EGF for label 1, which talks about or which specifies which item is put into the first cell. So it is e to the power x minus 1. So the whole system will have EGF e to the power x minus 1 to the power n. And now let us take a closer look of what is e to the power x minus 1 to the power n. Now this is very interesting. So first of all, we are expanding this using the binomial theorem. Okay, we have mentioned binomial theorem in the tutorial just this week. Yeah. So it is going to be the summation of j equals to 0 up to n. So we actually can put it into infinity, so it doesn't matter. So, but let's stop at n. N choose j. And then we have what? We have minus 1 to the power j, and then e to the power x to the power n minus j. Is that okay? So in order to get a total of n terms in the exponent, we would be choosing n minus j of this one, and then j of this one. So altogether, we have n terms selected. So there are n choose j ways of doing such a selection. And now we have ex n minus j. So this time we are expanding this particular term. Yeah, this particular term. Yeah, I cannot show. Yeah, this particular term based on the definition of e to the power something. So it is 1 over r factorial multiplied with the exponent to the power r. So n minus j r x r. Okay. And after that, we can do the rearrangement of terms. So we can put the summation very early, and then we can put 1 over r factorial xr before this j because they are independent of j. Is that okay? So after rearrangement, we get this one. Yeah. So the way that we get this one is, so we can see it clearly. It is going to be the summation of xr over r factorial multiplied with this part. And recall that the desired number of permutations is we get the coefficient of x to the power r multiplied back with r factorial. So what does that mean? It means that the desired number, so we didn't give it a name, the desired number of arrangement is this term, is the summation of n choose j minus 1 to the power j n minus j to the power r. So this term. So the number of r permutations of n distinct cells, each cell appearing at least once, is this term. And this term, we can see that it is a multiple of n factorial. We can show this by a symmetric argument. So by relabeling the cells in different ways, so there are n factorial ways of relabeling the cells. So each case that it happens in a particular label will also happen in another label. So we can group the arrangement of items or the distribution of items according to how they distribute, forgetting about the labels, together in the same group, so that each group there are exactly n factorial of them. So in that case, ARN, you can group them so that each group has n factorial, and then it forms distinct a partition of the whole number of arrangements into these kind of groups. So what does that mean? So the total number of groups is the value of AR over ARN divided by n factorial. So we call this number SRN. So what does SRN physically means? It is just saying that it is the number of arrangements of R items into cells, into n cells, but then these cells are non-distinct this time because we are not caring about the labels. But then each cell must have at least one item. Okay. By the way, the value of ARN here you can obtain this by using the method that we have just shown, but then you can also obtain this by using the combinatorial argument, by using the principle of inclusion and exclusion. So think about this. Yeah, we may be talking about this in the next tutorial. Okay, SRN itself is called the Stirling number of the second kind. And then this table actually gives us some of the values of SRN. And SRN follows a very nice recurrence relation. So we would, so let's make it into your next homework. So you will see how can you express SRN based on the previous terms. So it is very similar to something, the Pascal triangle, but with a different formula. Okay, now, so if you want to look at a little bit more complicated case, so this time we are supposing that we have our objects in total, and then we want to put them into non-distinct cells, but let's say we don't have any restriction of the number of items in the cells. So previously, we must restrict that the item in each cell has at least one item. So there is at least one item. But here, it can contain 0. So how many ways are there? So to obtain the results, we need to be very careful, okay? Yeah, because because cells are not distinct. Yeah, so let's say if we are just using 7 cells out of 100 cells, so the cells without labels, they do not, so any time that we are using exactly 7 cells, so we don't care which 7 of them are. So in that case, what we can do here is we can do the counting by using the rule of thumb. We divide the problem into different cases. So the first case is we just have one non-empty bin. The second case is we have exactly 2 non-empty bins. The third case is we have exactly 3 non-empty bins, and so on and so forth. And then we count the number of ways of distributing the items into these cases. So in that case, we sum them up. This is the answer. So it is SR1 plus SR2 up to SRN. Is that okay? And notice that, okay, strangely speaking, we cannot do something like this one as before. So here, what we were doing here is we assume that we are counting the cases when the cells are distinct. And then once we have counted the number of ways that the cells are distinct, each containing one item, we divide the value with n factorial. But we cannot repeat this with the case that we are counting with n cells without any restriction. So if we have n cells without restriction, the value will be n to the power r, right? But then n to the power r, you cannot just simply divide this by n factorial and then get the answer. Yeah, I think this is explained in the lecture. But then if you haven't watched the video yet, it is a very good idea to check your understanding. Why we can't do the same process. Finding the number of ways when we have when we are going to distribute the items into distinct cells and simply divide the answer by n factorial. So previously we can do so, but now to obtain the solution for this one, we cannot do so. We need to separate this into different cases and add them up. So this is something interesting. And then, so now, this is a simple recall of what we have just, so this is e to the power x minus 1 to the power n is the exponential generating function of dividing or distributing r distinct items into n distinct cells. But then we just mentioned that the number of ways here, ARN, is n factorial multiplied with the Stirling number of the second kind, SRN. Okay, so based on this, we will see that, okay, if we check this particular formula, this is a very strange formula, ex minus 1 divided by 1 factorial ex minus 1 squared divided by 2 factorial, ex minus 1 cubed divided by 3 factorial, and so on and so forth. Yeah, and so on and so forth. Then what? Then this one, the coefficient of x to the power r divided by r factorial will be equal to this term. Now, this is not exactly the same term that we are looking at because we are now stopping at SRN, but somehow it is still related. Is that okay? So suppose that this time when we have R is less than or equal to N. If R is less than or equal to N, then what will happen? Then we will have the terms here, a bunch of terms here, that is in the end will be 0. Then this will be equal to exactly this one. Is that okay? So for the case when R is less than or equal to N, the value of the summation of this one will be equal to the coefficient of xr divided by r factorial in this expression. Is that okay? So in a very particular case, when r is less than or equal to n, we actually can find out the exponential generating function for the counting problem. And then this particular exponential generating function can be nicely or complexly described by this function e to the power x minus 1, and then this term the minus 1. Is that okay? Okay, I think that's all for the summary for today. So if you have any questions, yeah, please send me emails or let me know now. Okay, so yeah, thank you very much. Yes, very good. Yeah, I saw a comment. Yeah, that's perfect. Okay, that's all. And then, yeah, see you next Tuesday. Okay, bye bye.